So today, talking about the last part, the last two sections of our chapter 11, limiting reactants and percent yield. And basically what we're looking at here is we're still looking at limiting reactants as terms of our mass problems using our mole ratios, and percent yield will be trying to figure out how much we got out of how much we should have gotten. More like the idea, okay, I made 7 out of 10 free throws instead of what's my error, what percent did I make, that kind of idea. Okay, so as we start off here, first of all, as we look at limiting reactants, we have our definition that basically it's the reactant that's going to be used up in a reaction, and that used up reactant is what's determining how much product can be formed from our reaction. Okay. We're going to know, in other words, we're going to know both reactants, and we have to figure out which one is used up. And we'll start off with just a little bit of humor here today, and maybe end with some later on. Get the idea of what we're maybe taking a little bit of a look at today. And I know you're laughing really hard too. So again, we take a look at the limiting reactant, and what is it again? It's that reactant that's completely used up in your reaction. That's our limiting reactant. What's been used up? And that is what determines how much product is produced. The other substance that's not used up in the reaction, there's going to be some of it left over. Once the first reactant is done reacting, or once that limiting reactant is used up, your reaction is going to stop. It's going to stop. There's nothing else going to happen, and the other reactant will be left over. We call that reactant as being in excess. Okay? So no matter how much excess reactant we have, we can't do any more reacting. So what we end up with is we end up with a situation where we can make an amount of product from one reactant, and we can make another amount of product from the second reactant, but if we pick the wrong reactant, we're going to say we're making a lot more than what we can because that reactant won't be used up. And that's the idea here of what we're trying to do is we're trying to figure out which substances are limiting reactant and then using that in order to find out how much product can be formed. So, as an example here, we have our little demonstration here. We have a couple of boxes of cake mix and some eggs. And our basic recipe is going to be that for one batch of brownies, or one pan of brownies, it's going to take one box of cake mix and 2 eggs. So if I have 2 boxes of cake mix and 12 eggs, how many batches of brownies can I make? Obviously, you can see in the picture is that you're only going to be able to make 2 batches of brownies. One of our substances is used up completely, that's the cake mix. The eggs, there's 8 eggs left over because it only takes 2 eggs per box. Now if I went by the number of eggs, I could say I would have 6 batches of brownies, right? Not just 2. So what we have is our difference between our reactant, our limiting reactant, and what's in excess. So we're going to make sense of limiting reactants here a little bit. We don't want to be confused. We want to be able to figure out what's going on. So basically what we're looking at as we look at a limiting reactant problem is we're going to be able to tell it's a limiting reactant problem because we're going to be given the mass of both reactants. They're going to tell us this is the mass of the first reactant, this is the mass of the second reactant, and we're going to be looking for a mass or maybe a volume or moles of the product or one of our products. So that's your tip-off. You know both masses of both reactants. So what we're looking at is we're really looking at this very similar situation to what we've just got done doing in our first 2 sections with mass problems. But what we're doing is we're expanding it. We're going to do a mass type problem using our mole ratio in order to find our limiting reactant, and then we're going to complete our mass problem by using the limiting reactant as the substance. So we're figuring out which substance can we use to find how much product we're making. That's all what we're doing in this case. So if we look at this example, again, just another simple example, if I have 8 cars and 48 tires, how many cars could I actually make? Well, obviously you can tell real quick, each car needs 4 tires, 8 times 4 is 32. Okay, I'm going to use 32 tires up. And once I've used 32 tires, my car bodies are all gone. Once my car bodies are all gone, I can't make any more cars. There's going to be tires left over. So tires are our excess, and our car bodies are the limiting reactant. So how many cars that can be formed are dependent upon how many car bodies, not upon how many tires. So tires are the limiting reactant. Oh, tires are the excess. The bodies are the limiting reactant. Let me fix that up here very quickly. Turn on my bamboo. excess for excess. Okay, so how do we find the limiting reactant in a problem? What exactly are we going to do? Well, what we're going to do are these basic steps. We're going to find the moles of each reactant. If we're not already given that, we may be given a volume, we may be given a grams, we may be given a moles. If we don't have moles, we need to find how many moles of each reactant we have. Okay. Then, very carefully, listen to this carefully, we're going to use a mole ratio. We're going to take our first reactant's moles times the mole ratio of our second reactant to the first reactant. And again, the mole ratio means we're using the coefficient moles. So it's going to be the coefficient moles of our second reactant over the coefficient moles of our first reactant. And when we multiply that by the moles of our first reactant, that's going to tell us how much of the second reactant we would actually need if we want to use the first one up completely. Okay, so that's what we're doing. We're just doing this out of convention's sake. We're trying to do the same thing every time. It makes it simpler. We're always going to take the moles of our first reactant times the mole ratio of second reactant to first reactant, and that tells us how many moles of the second reactant we need to use up the first one. Then we're going to compare that amount. We're going to say, okay, this is how much I need to use my first reactant up. How much do I actually have of that first reactant? If we have more than what we need, so in other words, that number that I needed of my second reactant was actually smaller than the amount of first reactant that I needed, that I had present, then the first would be my limiting reactant. So it's like saying, okay, if I have the car and the tires, if I only had, I had 16, I needed 32 tires, but I had 48, so I needed less than what I have, so the bodies were my limiting reactant, not the tires. I have more than what I needed to use, so there's going to be some of that left over. If there's less of your second element or reactant than what you need, so in other words, if I only had 8 tires in that last example instead of 48 tires, then I couldn't make 8 cars. I can only make 2 cars. Then tires would be my limiting reactant. So if you have less of the second reactant than what you needed by what you just found, the second is your limiting reactant. If they're the same, if how much you have and how much you need are the same, then it doesn't matter. They're both going to be used up in your reaction. You can use either one to calculate your product. And then finally, once you know your limiting reactant, then you complete your problem by using the limiting reactant to multiply it by the mole ratio of the product to the limiting reactant to get your substance. And then you finish off the mass, if you, that's or volume, whichever one you're looking for. So here's an example. If 24 grams of hydrogen react with 34 grams of oxygen, how much water could we form? And the balanced equation is 2H2 plus O2 is 2H2O. Now, if I do like we did before and I put my values in my reaction, they're going to tell me what I have, what's given, and what I'm looking for. And that will look like this. Notice this tells me, hey, look at that. I have both reactants. I have hydrogen and I have oxygen. I have 2 values. Which one do I use to find the water? The question is, we have to determine that because that tells us limiting reactant problem. So we said the first step was to find the moles of each substance. So we're given both reactants masses. That's telling us limiting reactant problem. So step 1, find the moles of each reactant. And moles of each reactant is just going to be grams divided by the molar mass for each one. And for hydrogen, that's going to be 24 grams divided by its molar mass, which is 2. I'm not showing how to do molar masses here. I'm assuming that we're pretty good at that. Hydrogen is 1 times 2 is 2. Oxygen, O2, is 16 times 2 is 32. We divide those values, and we get 12 moles of hydrogen present. That's how much we have in our reaction, and 1.06 moles of oxygen present in our reaction. That's what we have. Okay, that's step 1. Find that. Now, we're going to take our first reactant, just out of convention's sake, to do the same thing every time, and we're going to find out how much oxygen do I need to use up all my hydrogen, and then compare that with that 1.06. Okay, again, so find how many moles of oxygen is needed. And what we do again is we just take those number of moles of hydrogen that we have, we multiply it by the mole ratio of our second reactant to our first reactant, given to given in this case, because we want to find out how much oxygen do we really need. So that's 12 moles times 1 mole of oxygen to 2 moles of hydrogen. Those numbers, again, are coming from the balanced equation. Excuse me. It hasn't been that long yet, just I'm taking some time. And that would give me 6 moles of oxygen needed to use up all my hydrogen. Okay, so I need 6 moles. To use up all my hydrogen, I need to have 6 moles of hydrogen present, or 6 moles of oxygen present. How much do we actually have? That's the next key. We compare how much we need to how much we have. Now in this case, we need 6 moles of hydrogen to use up all our 6 moles of oxygen to use up all our hydrogen. But we only have 1.06 moles of oxygen present. Do we have enough oxygen to use up or make all of our hydrogen react? No, we don't have enough. So therefore, once I've used up that 1.06 moles of oxygen, some hydrogen is going to be gone, but there's going to be a bunch of hydrogen left over. So hydrogen is our excess material. Oxygen will be our limiting reactant. So how much water we can form is dependent upon how much oxygen there was, not on how much hydrogen. And so then to finish off the problem in this case, we use our moles of oxygen to find out how many moles of water and then how many grams. So I already know moles, so I don't have to find moles again. That's kind of the nice thing here because we've already found number of moles. But then we just take times our mole ratio, which is 2 to 1, 2 moles of water to 1 mole of oxygen, which is 2.12 moles of water. And then grams is moles times molar mass. So moles of water times the molar mass of water, not of oxygen anymore, would be 18, which is 38.2 grams of water. Okay, that's a limiting reactant problem. We find which substance is used up and then use that substance to find our product. Okay, if we had used the moles of hydrogen to find the grams of water, which I'm just going to pick the first one just because it's easier and I know what I'm doing, then we ended up saying that I could have made 216 grams of water. That's a lot different than 38 grams of water and is basically a very wrong answer because the hydrogen is not used up. We have to figure that out. Okay, on to percent yield then quickly. And percent yield, we're just, as I said at the very beginning, it's that percentage of product that we get from our reaction. If I shot 10 free throws and made 7, what percent did I make? Not percent did I miss, what percent did I make? It's what my success rate is in this case when we talk about percent yield. And that would be 70% in the example. So we're comparing our experimental yield. We call 2 terms that are very important here. Experimental yield. That's what we actually found from doing the experiment. We did the experiment. This is what we measured at the end. We compare that experimental yield with a theoretical yield. The theoretical yield is what we get from doing a mass-mass type problem using the balanced chemical equation. So the limiting reactant problem we just did, the other stoichiometry sheets that we've done before, those are all percent yield problems, or our theoretical yields. And then your percent yield is very simply found by taking how much we got out of how much we should have got, actual divided by theoretical, and multiplying by 100. Now in our percent yield problems, they will always give us the actual yield. So we won't use that to the very end, but we have to generally find, by doing the same types of problems we've been doing, your theoretical yield. Now simple examples here first of all, I believe. I'll actually do a little joke first about percent yield, which could be some of our lab results. Give you a second to read that. 0% yield. Just kidding, because we do better than that. Here is an equation. We have ethanol is produced from the fermentation of sucrose, C12H2211, in the presence of enzymes. So the equation, the balanced equation, is C12H2211 plus water is 4 ethanol, C2H5OH is ethanol, plus 4 CO2s. So here what we're looking at is if we want to determine what the percent yield is, if we used 684 grams of sucrose, C12H2211, and we formed 349 grams of ethanol. So that 684 grams of sucrose, that is going to be how much given substance we had. The 349 grams of ethanol formed, that is not an amount of reactant here. That is the C2H5OH. That is the actual yield. We have to find out, before I find my percent yield, how much should I have gotten. That's how much I got. How much ethanol should I have gotten? Okay, so here's just our reaction again, and here's what we have. We have the 684. We're looking for how many grams of ethanol can be formed. We're looking for that theoretical yield. We already know the actual. We're not going to use that actual yield to the very end. So we're going to basically just do a mass-mass problem. We're going to say, okay, I have 684 grams of this. How many grams of this can I make? So what's our first step? Find the moles of sucrose. So that's grams divided by molar mass. 684 divided by the molar mass of C12H22O11, which is 342 grams per mole. You can check that on your own, make sure that's correct, which is 2 moles. Okay, so I have 2 moles of sucrose present. How many moles of ethanol do I have? We find that by our mole ratio. So I multiply my moles of sucrose by the coefficient moles of what I want, which is ethanol. Whoop, pull that back down. Over the coefficient moles of what I have, which is sucrose, which is 4 to 1, which tells me I have 8 moles of ethanol. But I need to know how many grams that is. So grams is moles times molar mass. 8 moles of ethanol times 46 grams per mole. My 46 kind of disappeared there. So let's see if I can put that back in again. 46 there. And that is equal to 368 grams of ethanol. That's my theoretical yield. That's how much I should get from this reaction. Okay, so that's what we're looking for. We need to have that value to find our percent yield. So our percent yield then is our actual over a theoretical. They told me what we actually got when we did this reaction was 349 grams. We just found out we should have gotten 368 grams. So we take that, divide, multiply by 100, and we have a 98.4% yield for this reaction. We got 98.4% of what we should have gotten. And really, there are a lot of different reasons why we don't get 100% yield. We might have a reaction that doesn't go to completion because of conditions, like there's too much air, not enough heat. There's a different product that's been formed. We saw one lab earlier where we could have made, for example, magnesium oxide or magnesium nitride, which would reduce your percent yield of magnesium oxide, if that's what we're trying to make. So there's lots of different things that can happen where you're not going to get 100% yield. Some reactions are really tough to do. You don't get 100% yield from them. In fact, in college I had one reaction that I had to do for a project where you were lucky to get 50% yield. And that's the actual production method of it. You're only going to get 50% yield in that reaction. And don't worry, the end is near. Of this lecture, not of all time. What can I say? And that's how I feel sometimes in class. I'm probably going to do a video like this because I don't know if you're chuckling or laughing or not. So that's kind of what I feel there. Okay, and so that's all for today. We'll see you next time.